we're going to talk about Taylor polynomials and Taylor series in this unit. And there's a lot of words on this page, but I just want to try to bring some things to the forefront to kind of lay the foundation for the unit. So the idea of series in general are a little bit nuanced. There's a lot of little wrinkles to this. It can be a little troublesome for kids, but here's the baseline. Series and Taylor series and power series arose from this early need to get good approximations for functions such as sine and cosine and really transcendental functions in general. So anything that transcended the use of algebra, such as logarithms and exponentials and trig, we needed an expression for, because remember, when they were developing this math, they didn't have a calculator, they didn't have computers. So how are they going to get approximations for these values without having some sort of system in place? Now, they were developed over thousands of years and all of these things, they kind of explored what was happening in the universe. But we've talked a lot about convergence and divergence over the last few weeks. And it's really important that you understand that convergence is necessary because it guarantees that you have a good approximation for the exact value of your function if you use enough terms. So if I'm going to use power series to estimate a function, right, to try to get as close as I can to that value, I need to know if the estimation is good or not, and that's where convergence and divergence comes in. So now, there were a lot of things being discovered whenever they developed Taylor series, but the beauty of a power series is that it is always going to be easy to differentiate. Let me highlight that actually. It's always going to be easy to differentiate and integrate. So let me give you an example of that. There is no such expression for the closed expression of the antiderivative of e to the negative x squared. If I asked you to integrate this, you couldn't use U substitution, you couldn't use IBP, you don't have an expression that represents this. But what if I told you that e to the negative x squared can be represented by what we call a Taylor series, right, or a power series, and this is the same as this? Now, obviously with an infinite number of terms, because if you only use 4, they're not going to be exact at some point. Okay, I need an infinite number of terms, but this is pretty good start to give me a decent estimation. So what I can't do is integrate e to the negative x squared and get a closed form expression. What I can do is integrate 1 and get x, and integrate x squared and get x cubed over 3. So, and remember, 2 factorial is just a number. So 2 factorial is 6, right? So whenever I multiply, I add 1, I multiply by 1/5, I still have the 2 factorial. So factorials represent numbers, so you can get an expression for the antiderivative of this without getting its closed form expression, okay, which is interesting. But that is one of the main reasons why we use and study series, is because of that ability to derive and differentiate and integrate. Okay, there's lots of different uses for this. We're going to get into those. Again, I'm not going to read this whole thing to you. All right, but honestly, series were developed first. Before they ever had an understanding of integration and derivatives, they had an understanding of series. Mathematicians did. So if we were kind of teaching this in the order of discovery, we teach series first. But because we're trying to give you an ease in, we do series after we already have a foundation for derivatives and integrals. So let me expose you to this. All right, so we've got a Taylor polynomial and a Taylor series. All right, we're going to look real quick. We're going to explore this I'm going to use Desmos in the calculator. So I'm going to graph sine of x. And I'm also going to graph this little polynomial expression here. And I want you to see what happens. Let me see if I can get to the right Desmos piece. Okay, that's not the one I want. I want this one. There we go. Okay. So that is the graph of sine of x. If I also graphed that blue graph, which is the first 3 terms of a power series, the blue and the red perfectly coincide until I'm getting kind of right in here a little bit past 2. You can see that the blue diverges away from the red graph. Notice my terminology usage here, right? So notice the same thing happens over here a little bit past -2. So what happens if I add another term that fits with the same pattern? So there is a pattern to this x cubed over 3 factorial, x to the 5th over 5 factorial. So the next term is negative x to the 7th over 7 factorial. So I'm going to leave the blue up for just a second. So here is the green. So I added another term, and that green graph coincides with the red graph for longer. So its interval where the green graph corresponds to the red graph or converges to the red graph is longer, right? So I'll take the blue off. So obviously the green is more accurate. If I add another term, right, now the orange converges for a longer interval than the green does, right? But these are the exact same graph until we get to a certain x value, right? Kind of somewhere, looks like maybe around pi-ish, right? I'm getting that orange graph's getting a little bit off that red. That's what Taylor series allow us to do. And today we're going to talk about just the polynomial part, but Taylor polynomials and Taylor series allow us to do. So let's write a few things down in our notes here. All right. So the functions coincide around the origin for sure. Okay, so they look to be the same graph for a certain interval. I don't know exactly what that interval is because it's changing based on the more terms I add, right? So for me to create a larger interval where these polynomial and the sine of x function coincide, we would need to include more terms to be more accurate. So include more terms to create a larger interval. Now, there's a lot of exploring that we could do around error and around how this definition of a Taylor polynomial was developed. Honestly, if I taught BC to all kids who'd already taken AB, I would do a full day on how this was developed. But instead of that, I'm going to give you the definition of a Taylor polynomial. What we are doing is we're approximating the function by using, you can use T for Taylor, you can also use P for polynomial. I see both pretty regularly. A polynomial with a certain number of terms. Okay, and this is how it's developed. Okay, the C is what we would call the center. So the center up here was 0. Okay, I'll go back to the graph. So the center here, okay, was at 0, 0. Right, I hadn't shifted my sine function over. Okay, I was starting right there. So we do have a center to all of these. So you want to start at just the function at the center value. Then you're going to add the first derivative times x minus c. Now this is going to look like there's no, sorry about that. This is going to look like there's no pattern, but there is. I'm going to show you this. Then you're going to add the second derivative at c, excuse me. Now notice all of these are going to be values, right? Because the center is going to be a number. So the second derivative at 0, second derivative at pi over 2, second derivative at 4, right? Like those are going to be numbers. But then you're going to have x minus c squared divided by 2 factorial. So now let me go backwards for a second because it looks like where are we getting all of this? Technically, there was a 1 here, and it was also being divided by 1 factorial. But we don't need those because raising to the 1 power and dividing by 1 factorial doesn't mean anything. It doesn't change that expression, right? That term. We also had x minus c to the 0 here, because x minus c to the 0 is 1, divided by 0 factorial. Right? We had that. But again, we don't need to show that. That's not necessary. But that is part of the pattern. So now that I have a better feel for the pattern is plus third derivative at the center, x minus c cubed over 3 factorial. Now, we're going to do a lot of these, and today we're just going to talk about polynomials, but we are going to get to the infinite series part. So we're going to have the nth derivative, x minus c to the nth power, all over n factorial. So that is the form or the general term, okay, the nth degree Taylor polynomial at c. All right, now, we don't need, I'm going to mark this out in gray. We don't need this, we don't need this, we don't need this, we don't need this. But it does help you develop the pattern a little bit. I realize that looks crazy. I promise you this is going to make sense. Now, we do have a situation where c is 0, right? So if the c is 0, then that means all of these, right, I'm sorry, right here, is just x to the 1, right? X squared, x cubed. So we like these. These are called Maclaurin series. They have a special name. I don't know if you remember when we did MVT, but we had Rolle's theorem. It's like he just wanted his name on something, right? This is kind of that all over again. So let's do, get me a slightly different color here. Let's do the formula for a Maclaurin series. We're approximating. You could call this M. You could also call it P because it's going to be a polynomial. And we would go, the center is 0, so f of 0 plus f prime of 0 times x, because it's x to the 1, plus f double prime of 0 times x squared over 2 factorial. Told you factorials weren't going to go away, right? Plus the third derivative at 0, x cubed over 3 factorial. So again, the general term is the nth derivative at 0, x to the n over n factorial. Again, that's Maclaurin series. So right now we have a formula for a Taylor polynomial. I got to stop saying series because today we're just talking about polynomials. Taylor polynomial and a Maclaurin polynomial that we're going to develop in order to help us find values for things like sine of x or other transcendental functions.